everyone. Okay. Welcome to the 18th EAI QSHINE 2022. This year, this conference is co-organized by the EAI Society and Chongqing University of Post and Telecommunications. I'm Zhao Longning from the CQUPT, and welcome all to join the conference. First of all, this is the video sent from the organizer of the EAI community.
Gentlemen, welcome to EAI QSHINE 2022. My name is Ivana Bujdakova, and I would like to address all of you on behalf of EAI. I would like to thank all of you for being a part of this conference and for your involvement with EAI. Above all, I would like to thank the general chairs and the whole organizing committee for their excellent work during the conference preparation. I invite you to join us again next year at the EAI QSHINE 2023. We will keep you updated, and the news about the event will be announced on the conference website soon. Should you be interested in becoming a part of the next year's conference, please do not hesitate to contact us at the email address below. If you are interested in discussing other possible cooperation, conference, a workshop, or a new event altogether, please contact us at this email address.
Okay, here is the main program of this conference. The first part is the keynote speech. First, let me introduce the keynote speaker, Professor Song Guo, and the title is Neural Enhanced Edge Perception Systems. Professor Song Guo is a full professor leading the research group of networking and mobile computing at the Department of Computing, the Hong Kong Polytechnic University. He also holds a Changjiang Chair Professorship awarded by the Ministry of Education of China. Professor Guo is a Fellow of the Canadian Academy of Energy, Fellow of the IEEE, and ACM Distinguished Member. He is the current Editor-in-Chief of IEEE Open Journal of the Computer Society and Chair of IEEE Communications Society, Space and Satellite Communications Technical Committee. Okay, let's welcome Professor Song Guo to give us the keynote speech.
Thank you, Professor Ning, for the kind introduction. So I will first to share my screen. Okay, could you see the screen now?
Yes.
Okay. Thanks again for the organizing committee to invite me for the conference. Actually, I have been helping the EAI conferences a long time ago. And today I'm very happy to be back, especially for the events hosted by the Chongqing Post and Telecommunication Universities. I have been visiting the university in the past several times. Many friends and colleagues are still in the close collaboration. So today I'm very honored to share some of my recent research on edge intelligence. Today I'm particularly I would like to report on the most current research results in the perspective of neural enhanced edge intelligence. My talk will have three parts. First of all, give a very brief introduction. What is the edge learning and a tiny machine learning system to help us understand how come from the traditional computing paradigm to the current edge learning and the tiny machine learning system. And the next part is a neural enhanced edge intelligence. We shall first identify some key issues, key challenges, and then followed for each challenge, we'll discuss some of possible approaches and how we address those challenges. And finally, we will introduce some implementation issues using our developed solutions to support artificial intelligence assisted edge computing applications in smart city in particular. And also, I will show some open issues for the future in the edge intelligence. So first, edge learning and tiny machine learning. We would like to give a very, first of all, give a very broad view how the computing paradigm evolved from the traditional way. And as we know, there are two main strain computing paradigm. One is centralized, the other is decentralized, right? And the centralized, we have witnessed a very old mainframe to the modern cloud computing paradigms. In parallel, there's another distributed computing paradigm like early PC, client server mode, and later on to P2P computing and IoT computing, right? So the time comes to 2020, and actually these two main strains has both developed a very mature, and they merge together, and we will see a new paradigm is called cyber-physical system, right? So we would like to use the resources in the cloud and also use the IoT to interact with the physical world. So in the next 10 decades, that is the further development on that perspective, and we have a system called cloud, edge, and synthesized computing. So this is a combination of cloud computing, edge computing, and IoT computing. So in the next 10 years, lots of new applications, especially some AI enhanced applications, enjoy the benefits from both rich resource cloud computing and also other devices, lightweight devices around users. They can provide much faster responses. So two benefits will merge to help people enjoy the benefits of AI edge intelligence. So now, if we look a little bit close in the past 10 years, then there is a transition from the cloud intelligence to the current edge intelligence because of the three major factors, or you can see the requirements from the new applications like autonomous driving, industrial 4.0. The requirements is that the decision must be made in the real time, or the decision from the second level to the millisecond. Otherwise, the decision results will be useless, right? So that is one of the reasons. The second reason is some application in the past are relying on the accumulated data in the cloud to support application like a Web 2.0 services, like Google services, Facebook services, right? They have the users uploaded contents, and they can do data mining, data analytics in the cloud, and they provide advanced recommendation services, for example. But nowadays, the bandwidth from the edge to the central cloud, the bandwidth increasing in a linear speed. But the content generation is in a exponential speed, right? So eventually, it did happen that it's impossible to upload all contents from end users to the central cloud, right? So in other words, the data cannot be uploaded. They has to be utilized in the local machine, but they will be still used in another distributed collaborative way to support big data benefits. Okay. The last reason is sometimes it's not because of the constraints of bandwidth, but just because of the privacy concern. The data cannot be shared, right? For example, the company, they maintain the data credentials of users, and those information is critical, right? They cannot be shared, and they has to maintain everything in local and only be used by the company, right? So all these reasons actually suggest another way, another potential way that the intelligence services can be still supported, relying on the big data, distributed big data in the devices, and also utilize the resources across central cloud, distributed edge servers, and also large number of devices, right? So all these resources will be utilized to support data-driven applications. So one of the solution, probably everybody knows the concept of the federative learning, right? So the federative is a very representative solution that data will not be shared. Instead, the machine can run their local optimization problems to train some machine learning models, and eventually they will share the models across a number of devices. The basic idea is that data will not be shared, but just the model will be exchanged through a node called a central server. You can imagine that there is an edge node, edge server. They can accumulate the local trained model and do some average on the parameters, right? And then they will distribute the generalized model to everybody. Okay, so eventually each node can use the machine learning model for more general challenges, because the model is not trained upon the owning data, but also a large amount of data from multiple participants in the federative learning, right? So this is solution, edge intelligence paradigm. The expanded paradigm is that we call edge learning, which enables distributed edge nodes to collaboratively training models and conduct inferences with the local data. Okay, so definitely the client server mode just in the parameter server is one of the solution. Other ways that some nodes could be in a collaborative manner, or there is no server. All of them are servers like a P2P, right, to do the machine learning tasks. So relying on the local distributed data, relying on also a large number of edge device, just like I just showed us an example of Huawei edge AI devices, Atlas series. This devices can be deployed in the smart campus. For example, they can embed it with the smart camera. Eventually, they can do machine learning, edge learning jobs for road traffic detection, parking lot finding, and so on. So this is, we understand how edge learning and how tiny machine learning comes from, right? This is because we witnessed that a very extensive interaction of people with the environment to enjoy the rich resources in everywhere to support the AI applications. Because those data devices, a large portion is close to users, the devices and the data increasing exponentially. If we can manage the resources data in a very efficient way, equivalently, the data seems like to be utilized in a central manner to support various of applications, right? So this is a view, and to realize, to implement the potential capacities of edge intelligence, and we need to take a deep look into the whole system, identify the challenges that we must be taking care of before we can eventually support applications in smart city, for example. I just take one represented paradigm, computing paradigm, as I mentioned, client server. You will see the client set is the bottom figure. Many clients, for example, the cameras, right? The embedded systems, the sensors, the wearable devices, and so on. You can imagine what kind of computing units with reasonable resources in computing, in communication, in storage, right? They have some local data. They can train on the local data, and they can also exchange the local model to others, right? And the server side, you can see is any devices from the edge to the central cloud. The simplest way is that we have a server, just one hop away from the users, just co-located with the base station. So they can cover relatively a large number of users. They can receive the parameters from clients, and they can do parameter aggregation, and they can broadcast aggregated parameters to all the clients in this coverage, right? So we have two tiers. Now, from the bottom, the client side, we will see in order to enjoy the big data benefits, right? We have to encourage as many participants to join as possible. So a challenge here is that we need to design some incentive mechanism to attract. Obviously, the mechanism should be provide a fair marketplace, right? The contribution from clients in terms of their local data, right? Their local computation, communication resources. The benefits is that eventually the model created can utilized to more general cases, right? That is very useful than the model created based on the local data. So lack of participants is our concern. The second challenge is the client is highly diverse in their physical, in their hardware configuration, right? Some devices you can see they have high configurations, right? For example, there are AI chips and not just doing the inference, but can also help to do the machine learning training, right? But other devices could be very high lightweight. They can have very limited memory. For example, a deep learning model cannot even be placed inside, right? So all these diverse devices has to be collaboratively joining in this edge learning system. Another heterogeneity is the data. Some devices, the data distribution is highly different to others. For example, this guy has the data with the unique label, right? Others don't have, right? So if the data distribution is different, how can I guarantee that the collaboration will achieve a model with high quality, right? So this is heterogeneous environment challenge. The third is also related to the clients because the resource is extremely constrained. As I mentioned, some machine cannot even hold the whole deep learning model, right? Because just simply the memory is limited, or the communication between the devices with the clients is limited. We cannot exchange too much parameters, right? So this is about resource constraints. Majorly is about the computation limitation, right? Now we look at the interaction across clients. You will see communication in particular, we have to pay more attention because nowadays the model has become bigger and bigger, right? If we still rely on the traditional parameter exchange methods, definitely that will still consume a large amount of bandwidth. Lastly, is about the whole system, right? Most of devices are lightweight. There is no much defending mechanism can be equipped either in a very complicated mechanism or the dedicated hardware. So you have to consider some protection in the security and the privacy to support the edge learning. All right, so in the following discussion, because of time, I cannot cover all the challenges, but I would like to pay a little bit attention on heterogeneity, on computation constraints, on communication constraints, and privacy, 4 issues. And for each issue, I will just showcase some approaches that we have tried. And as an example, to help you understand, we identify the challenges and then we formulate some problems, and then we provide solutions. And this is just examples. We are not, we are inspired people to see more advanced technologies to address those challenges. So the first challenge is about the heterogeneity. Heterogeneity, as I mentioned, the configuration of devices are highly totally different. Some devices like I just showed the ARM chips, right? And there are some devices is providing optimized performance. Others just provide fast responses or very low energy consumption, right? So all different devices will collaboratively doing the machine learning tasks. Another heterogeneity is that the data distribution is highly non-ID, right? Identical distribution, non-ID distribution. So to address this issue, I'm not going to explain all possible solutions. For example, in general, the issue could be classified into a data-based approach. We would like to provide a general model that will be used for everyone. Another approach is that on top of that, we would like to extract common knowledge, but we also want to make the personalized requirements. So in the following discussions, we're more interested on the second model-based approach. The trade-off is that we want to use the collaboration among a large number of users. On the other hand, the model will be customized for each individual node. Okay, so the basic idea is that the personalized model probably can be represented in a personalized model aggregation. This is our very intuitive consideration. For example, in this figure, we study four devices, 4 nodes participating in edge learning, right? For example, node 0, 1, 3, 4, okay? And the color in here, in blue, is client 1. Client 1 probably in the initial convolution layers, which normally do the feature extraction, right? And they probably do the aggregation from client 4, for example, client 3. The reason is that those clients have relatively similar data distribution to itself, okay? And if you look at the figure on the right, the full connection layer, they do not do any aggregation, okay? They use their own parameter instead, because the full connection layer normally do the classification job, right? And the classification is more related to the local job. So this is a very intuitive, and we do some experiments. Okay, on the left figure is the results doing the traditional model-wise aggregation, just like the federative average. This is the yellow line. And the blue line is using the approach on the right-hand side, using the layer-wise aggregation. And we do know that the client 3, client 4 probably is helpful. Client 2 is even unshown because the data distribution is totally different from the client 1, right? So indeed, you will see the figure that is much higher. The accuracy is much higher than the traditional way. So this is the first step. Now, in a more general case, how can I identify which clients or group of clients have a better have a similar data distribution, because data will not be shared, right? You have no idea which is helpful, the others is not helpful, right? So our formulation idea is that we probably can use some meta learning to help the aggregation in a way that they can be learned from the process of the edge learning. So we introduce a HyperNet in the server side. The basic idea is that the aggregation manner will be parameterized. as a vector, and then we can use the overall layer-wise aggregation to eventually not just to optimize the parameters on the general model, but also to optimize the parameters, the customized aggregation parameters for each client. So basically, we have the parameter upload, and then aggregation, and eventually the aggregated model distribution is very similar to the federated learning. But in here, we introduced the customized aggregation approach at the server side, still using the back propagation methods, using the gradient descent algorithm to optimize the aggregation parameters. And eventually, the model will show excellent performance. And the details I'm not going to discuss. Just show some of the idea. All right. Now we are dealing with the devices only considering the data distribution, not homogeneous, right? We did one step ahead to consider the hardware is also heterogeneous. The motivation is that some of the nodes with a very limited bandwidth, very limited memory, they cannot hold everything, right? So in here, we introduce a personalized model, right, to do the same job. Obviously, in this configuration, the model aggregation, no matter it's model-based or layer-based, it doesn't work in here. The topology are totally different. But we still use a very similar idea, doing the parameterized aggregation, not on the model, but on the logics, So in here, we introduce some public data set on each clients. They optimize their local model, but on the other hand, they will generate some logics, soft prediction, and then they will upload not the parameters, but the soft prediction to the server. And once again, the server will learn how to do the personalized aggregation for each devices and send back. And then the model, even though the topology of the model are different, they can still use the software, the aggregated prediction to update the whole model. Eventually, they can achieve enhanced performance. All right. So this is the second challenge, and we would like to particularly consider computation constraints. So before we discuss the approach, I just show some evidence, right? So for the embedded devices, the computation power is very limited, okay? For example, there is no high bit computing units. This is totally different from the rich high-end devices with 32 bits, right? They only have very limited bits. For example, only 8 bits on the chips, right? So the computation power is very, very limited. Others like the memory you will see is only 100 megabytes, is even lower than the size requirement for deep learning model, right? So how to deal with those challenges? Now we first look at the computation power, and first we would like to identify which part is more computation computation cost is higher in the overall bidirection passes. So we do the experiments and see the convolution layer actually took the most cost in the computation. So if eventually we just use the low bits chips to do the inference job, and then that is relatively easy because by using the quantization methods, for example, the 32 bits down to 8 bits, we use the formula scaling and rounding. We can do the quantization, right? So that can be easily implemented in the cloud by introducing on purpose a quantization error. Even though in the cloud we have the full precision units, but we on purpose to downgrade the 32 bits to 8 bits, right? But later on, the error will be not propagated because all the remaining computation is still relying on the 32 bits. By these iterations, the model will be converged and eventually they can be deployed in the real embedded system for inference only, because the quantization error is already considered in the training. But when the data, new generated data to help retrain or to fine-tune the model, so some of the training job has to be done on those devices. So what we can do, so in this very challenging issue, we actually come up with an idea that by introducing some additional neural network structure, we can actually support the quantization-based training. Okay, the basic idea is that we introduce parameterized range clipping technology to estimate the quantization errors in each iteration, and the estimated quantization error will be compensated in the next iteration. And in this way, the model can be converged. We can prove that it will be converged and then provide good performance. And we implemented our solution in the Alice, Huawei Alice AI chips, and you will see the computation requirements reduced a lot, and the accuracy still acceptable. So this is about the computation on the on the training, on the inference, for the case that we more focused on the number of bits in the AI chips is constrained, so we have to use the quantization. But even though this is the very simple case, but in the future, the solution is very promising, because you will see from here, they converge. Then compared to the non-quantization cases is still converge, and the accuracy with little drop. Another direction to reduce the computation cost, not just on the chips, right? We would like to on the model. So the basic idea is that if we can identify some redundant job, and then we just ignore, or we just skip those computation. And those computation, as I mentioned at the very beginning of this section, the convolution part is most expensive part. So in here, at each convolution layer, we introduce some skipping mechanism to skip some of the portion of on the feature map, and then we can provide speed up in the computation because lots of redundant or less important portions will be skipped. So in this way, the computation, even though the computation power is limited, we can still provide very good high performance training work. Okay. The third issue is about our communication. So in a very similar way that we just show what is the evidence, you say that communication is a bottleneck. This figure shows the complexity of model, right? And you will see nowadays is language model is very, very popular, right? And the number of parameters in the model is from hundreds of million to nowadays is billions or 10 billions, right? All these parameters, if you do the federative average, is impossible to exchange. Another overhead is in the synchronization. You will see when we have more users participating in the federative training process, you will see the synchronization time on the right side in yellow is sometimes increasing in terms of the number of workers, right? The original design is that we have to, at each iteration, we have to make sure all the contributions from the clients received, and then we go into the next round, right? So local computation, uploading parameters, broadcast aggregated parameters, 3 steps all completed, and then all the workers will go into the next iteration. And obviously this will take a long time because when more participants in the learning, there are more stragglers because of whatever software issues, hardware issues, networking issues, others has to wait them, right? And then the overall time in waiting is significant. So both traffic in terms of parameters and also the synchronization must be considered. In the following, we have discussed the approaches to deal with communication traffic and also the synchronization overhead. So for the traffic, basically what we can do is to do the compression, right? Either we do the compression like a quantization, right? We can just 30 bits parameter down to 4 bits, for example, right? So overall traffic could be much compressed. Or we can do less number of exchanges, right? We do push the local parameters and pull the aggregated parameters. We would like to make the frequency of such operations less, but the trade-off is that you have to consider in one hand, you save the bandwidth, but on the other hand, the performance should not be much compromised, right? So all that is the first category. For the synchronization, probably we need to consider some pipelining technologies, make the waiting time as minimum as possible, right? The traditional way for traffic frequency reduction or traffic load compression is already comprehensively studied. Today, I would like to talk about a little bit different in terms of by taking the special challenge in edge environment into our consideration that the traffic, the node has very limited memory. In other words, traditional parameter exchange takes some bandwidth, but other cases, because the model has to be split into multiple places, in this way, introducing another form of traffic is the intermediate data, right? Intermediate data in terms of the feature map. And this is possible in the split learning. And split learning is another way of edge learning, right? And in the intermediate traffic, how to do the compression. And this has been never studied yet. So in here, we introduce compression methods on a concept we called stripe-wise. We do the compression stripe-wise. So if you only use the traditional quantization methods, all the traffic, the feature map will be you will consider as the figure on the right is flattened at the pixel level, and then we do some quantization, right? But in here, because the object we are looking at for compression is the feature map, right? They have very unique characteristics. For example, in the figure in this page, some of the feature map in different channels could be highly similar with each other, right? So this motivates us to consider why not we group the feature map in different channels together, and we do the quantization on the grouped channel feature maps. That could be save a lot of traffic. So what we do is to introduce a channel attention mechanism into the backbone of the network, and we give a score on each channel, and the score with similar to each other. We will see those channel feature maps could be bundled, could be grouped together, and then quantization will be on grouped channels. And in this way, we can save. We can do a much higher compression ratio than the pixel-wise compression. Again, we implement our solution into the system, and we can achieve a good trade-off in the convergence and accuracy, and we can achieve very good performance, a very good accuracy, and we can prove using our methods the higher compression ratio achieved, and also the convergence can be guaranteed mathematically, right? And the traffic accuracy trade-off, you will see our methods. The blue lines is on the most left and the top location of the accuracy traffic coordinate system. So it implies that our solution can achieve the best trade-off. All right. So this is about traffic side. For the synchronization, as I mentioned, the best way, one of the way is to parallel to parallel the computation, or even the computation and the communication, such that the waiting time could be minimized, right? So compared to the original BSP, you will see here in the lower part, the communication in black and white bars is parallelized with the computation, right? And we can, in this way, we can achieve much performance gain. Now, if You see, this is the solution. We can achieve speed up by 5 times. If in a more complicated layered network, and we can also introduce the pipelining mechanism to reduce each iteration by 4 from 4 slots into 2 slots, which means some of the communication across 2 hops can be parallelized, right? So the time could be again shortened. All right, this is about communication. Lastly is about security and privacy. I show some of the challenges, right? The model attack, the data privacy attack, and so on. In particular, we cannot rely on very complicated, the traditional cryptography mechanisms, because normally they need a lot of communication, computation resources. In the edge, this is impossible. So now we look at a specific challenge is about the privacy leakage. So everybody probably heard about the gradient leakage attack. The basic idea is that the server probably after receiving the report from each worker, they can do a reverse engineering task to find out what is the raw data, right? So in this way, they still run the similar gradient descent algorithm, but they take the raw data as a variable, but the parameter as a constant, and using the gradient descent algorithm to find out what is the raw data, right? So using multiple iterations, I will see the recovered raw data is almost similar to the ground truth. So the privacy is released, exposed. Okay. So what we do traditionally, you can see probably you can introduce some noise, right? You can put some noise into the parameters, but this is not working when a relatively large amount of noises, because even though a large amount of noises can help protect the privacy, but the aggregation is working on the poisoned parameters. In other words, the aggregated model is kind of deviated from the optimal one. The performance cannot be guaranteed, right? So this is the traditional way. So our approach is that can we find a way that we can inject sufficient noises at each individual workers, but eventually we can still have a model to provide a high accuracy inference, right? So that is our job. We still we actually take a deep study on the issue and find a way that we adopt a technique called perturbation matrix theory into the federative learning. The basic idea is that we can recover the genuine model after filtering out the noises. Okay, so if we can control the distribution of noises in the server, and then we can filter out those noises. So the basic idea in the following 3 steps. First step, each individual will randomly inject some noises, okay? And second step, the original data will be aggregated inside of which the noises will be also aggregated, subjective to a given parameter distribution of Gaussian noises. Okay, the last step is to use perturbation matrix theory to fill out those Gaussian noises because the mean and variance of the distribution is known to the server. All right. So this is the basic steps, and we see that in this way the privacy is preserved. Okay, because we can inject noises compared to the others. This is very robust because traditional way, even though you can inject some noises, but if the attacker makes some smart decision by screening the layers with noises, then they can still do the recovery. But in our case, the noises is not just concentrated on particular layers. They can be everywhere. So use the traditional screening technique doesn't work in here. So we can provide high privacy. High privacy. Accuracy, you will see here, we can do almost the same accuracy as the one without any defense. In other words, there is no seems like there is no noises injected. So high accuracy can be still achieved. In terms of overhead, computation overhead, because we introduced a little bit compensation operations at last step, right? So you will see we have a little bit less than 10% of computation overhead. And this is acceptable compared to very computation expensive solutions. Okay. So we almost complete our talk. The last couple of minutes, I will summarize what we have done, especially when we're developing some real systems using our solution. So the whole framework, our study is that we develop the solutions in terms of data aggregation, privacy preserving sensing, and edge AI acceleration techniques. Okay, so using what we have discussed, like resource limited computing, right? Using a model quantization, model partition. And for the privacy concern, we do something like a communication, compression, cooperative learning. And for data management, we develop the blockchain technologies. On top of that, we support various applications like smart transportation system. On this project, we do collaborations with local universities and also Alibaba to develop technology for smart traffic control. Risk management, this project actually is collaborated with the local company and the civil engineering department. They can equip the edge devices on the worker and also the construction site to monitor the situation and do protection of the workers. And similar technology has been implemented in the in-car camera. They can do the monitoring of drivers for safe driving. And Another application is for smart healthcare, and we implement everything into a very small device. They can do screening. They can do a diagnosis of postures, and we can also implement our algorithms on the smartphone for regular use to do the diagnosis and also do the recommendations for the patients how to correct their postures. Okay, so this is some real implementation, and some of the successful prototype has been reported in the media. And in the future, we are today only consider the computing data model, but the developer, the AI supporter has to consider everything, right? You have to consider what model will be used, how can I train the model, how can I get appropriate data, and so on, right? You have to consider everything. In the future, our vision is that we will build a federated edge AI, and they will take everything in the cyber infrastructure to support various of edge AI services, right? So different services, you just give the requirements, and then the federated AI cyber infrastructure can do the job for you, like artificial general intelligence services provision framework. They do serverless computing. They maintain AI data house platform, and they can run the federated infrastructure in a decentralized manner using the smart governance technology. So this is the technologies that we are looking at, and we are take big efforts to implement. Most of the contents in this talk is available in our website, PolyU Edge Intelligence Lab. Many papers you can download from this website, and also many materials in our published textbook. One is on edge learning, the other is on tiny machine learning system. All right, thank you. I will stop here for questions.
Okay, thank you so much for the meaningful keynote speech given by Professor Song Guo, including the recent work from both the research and applications in the edge intelligence. Very, very meaningful and helpful. Thank you very much. Also, there's the anyone has some questions or comments for discussion? Okay, I will ask two questions. The first one, although you have mentioned some work about the literacy iterations for the synchronization about information synchronization, but I'm also concerned about for distributed scenarios, how to guarantee the synchronization. Will the waiting time be too long for edge devices? This is the first question, Professor Guo.
Okay, so actually, I will go to this page. Okay, so traditionally, we call batch synchronization. Okay, the reason we need to do that is to make sure that the convergence rate is acceptable. Okay, because if there's no control, the convergence cannot be guaranteed. In other words, if some of the workers provided information is too old, is stale information, then they will drag the model, the global model, from the optimal backwards. So eventually the model cannot be converged into the optimal direction. So in the early work, we have to wait all received information is up to date. Okay, so each worker use their local model to do the aggregate, to do the forward propagation, backwards propagation multiple times, and they achieve a better gradients, right? And then the gradients calculated is the most up-to-date gradients. Okay, in this way, we can make sure that the global model will evolve from the original place to the optimal model. So if there are many workers join the system, some of the worker probably their GPU, CPU configuration is low. They probably needs a long time, right? Others probably the I/O speed is low, and whatever reason, they cannot provide as fast as others, right? The server has to wait until all up-to-date information received, and then they do an aggregation and send out to all others. And this is the challenges we mentioned. This is the challenge we mentioned in here. In here, right? So if more users, for example, only 4 workers in here, then all communication time in yellow is very small, very tiny, right? Because the speed is not too diverse. If there are 16 workers involved, you will see if still use the traditional way, and the communication could be overhead could be significant, even larger than the blue one. Blue is the time on the local computation, and the blue is the synchronization, including both the waiting time and also the pull and the push operation time. All right, so this is the traditional challenges. Now, to mitigate the problem, what we think is that why not we let the faster workers go further without waiting too long, right? This is the basic idea. But you have to guarantee that the differences, the fastest and the slower, the pace should not be too much. Otherwise, there is no convergence can be guaranteed. So mathematically, we have to control. In one way, we let the parallelism as high as possible. But on the other hand, the pace differences should be constrained in a period, in a reasonable steps. And we do this just controlling the pace. And in this work, we let the communication and the work and the model local computation parallelized, which means I'm sending the information generated in the last round, which means I'm not report the most up-to-date information, but at the same time, I'm doing the job. I'm working hard to update the local parameters, but I'm not reporting the most updated parameters in a way that the waiting time with each other will be minimized, right? So this is the figure shown on the left figure. So communication can be parallelized, so waiting time can be further reduced, right? So eventually we can achieve a lot of benefits. We can support good accuracy, but 5 times speed up. The next example is that we can use the idea. To pipeline the multiple stage push and pull operations. In other words, the parallelized steps, some information inside is not most up to date, right? So there is a trade-off. I have to provide half new, half old information without waiting to each other, that everything is new, but we can make sure in this way, the waiting time is minimized, the accuracy is still acceptable, and overall trade-off is maximized. All right, that is a very simple explanation.
Okay, thanks so much for the explanation. Also, the other question is that regarding the synchronization of communication and computing, is it possible that for the tasks to be processed at the edge for edge devices, but is it is it possible that some tasks cannot be or for edge devices they would not like to process the tasks. That is, there are some tasks no devices will handle them. Will that happen?
Yes, that is another challenge. I mentioned, but I did not provide any solution yet. Is about I mentioned here is an incentive mechanism, right? Incentive means cannot
I see
large
here.
scale incentive driven client collaboration, right? If I cannot benefit from participating in the collaborative training, why join? Why join the work? If everybody think that way, and you cannot provide good job, everyone will only work on their own data. They will rely on their own models, right? But as we know, the data, the big data is another reason for the power of AI, right? If nobody share, if nobody can cooperate to willing to cooperate, and then the model only relying the local data cannot be generalized, right? That is the issue. But if you are interested in the topic, you can refer to what we published in the Infocom 2020 to address this issue. So probably you can design some mechanism. The basic idea is that the better data quality, the more computation resources, the time you have contributed in the federative learning, and then you have more rewarding, right? And then I use that approach to encourage more people to participate.
Okay. Due to time limitation, and I would like to thank you so much again for your explanation and the very helpful talk, keynote speech. Okay.
Thank you very much. Thanks
you so
again
much.
for the organizer, and then I appreciate it. And hopefully next time we can meet physically.
Yes, yes. Looking
Alright.
forward to that day.
Okay.
Okay,
Thank you.
so
And
much.
then if other people, other teachers are online and very thank you for your support and hope to see you soon.
Yeah, yes, thank you. Thank you. Hope to see you,
Okay,
Professor Guo.
bye-bye. Yeah.
Bye-bye. Bye-bye. Okay, the keynote speech terminates today, and we will back 10 minutes later for the accepted paper presentation.